Hello there and welcome to Lower 6th Further Maths, Pure Core 1 Past Paper, June 2012. We're working with question 10 here. This is a vectors question in which we have a context. So this is new to Pure Core 1, so I've added this question in myself. So what we have are planes A and B, and plane A has two positions and plane B has a position and a direction. In fact, this is probably a bit more useful than plane A, as I can write the flight path out for plane B using these two vectors. So it's minus 20, 35, 5, and the direction vector is 10, minus 2, 0.1. And what's going to happen here is that the coordinate for the flight path for B is going to vary depending on what value my lambda is. So if lambda is 0, it's going to be at this coordinate here. If lambda is 10, then I times this bracket here by 10 and add the coordinates onto the original position coordinate, and the plane can then move around. So I need to do this for plane A. What we're looking to do in this question is to find out when the two flight paths intersect and determine the vector of the point of this intersection. So what I first need to do is, if I call this coordinate x and this coordinate y, I need to find how to get from x to y. So you do coordinate y take away coordinate x, which is going to be 120 minus 80, 13, take away 220 and 5. So this is going to be minus 80 minus 108. So that's going to be the direction vector, and now I just need a position coordinate, so we'll use x, 225, add some lambda value of minus 80, minus 108. Now just notice here that I'm using two different letters as my scalar multiple on the direction vector. That's really important to allow planes A and B to start their movement at different times effectively. So what I'm going to do now is, if I have intersections between these two planes, then their x coordinate must be the same at a certain point, their y coordinate must be the same at that certain point, and their z coordinate must be the same at that same certain point. So I'll write those out. So the x coordinate for the first one is 200 plus minus 80 lambda, so take away 80 lambda, and that's going to equal the x coordinate on the second equation, because if they intersect they must have the same coordinates, so it's going to equal minus 20 plus 10 mu. For the y coordinate, this is going to be 20 add minus 100, so minus 100 lambda, which is going to equal the y coordinate on the second equation, 35 minus 2 mu. Excellent. So what I need to do, I don't need my z equation, I'll check that answer at the end, but what I'm going to have here are two simultaneous equations, so I've now just got to solve these simultaneous equations. What I think I'm going to do is I'm going to use this 10 and minus 2 at the end here to eliminate mu. So I'll keep this equation the same, we'll call that equation 1, and times this equation by 5 and add it onto equation 1. So 2 times 5 is going to equal 100, take away 500 lambda, equals 5 times 35 is 175, take away 10 mu. So we'll call this equation 3, and then we'll do equation 1, add 3. So 200 add 100 will make 300. Minus 80 minus 580 will take away 580 lambda. This one here, minus 20 add 175 is 155. And 10 mu take away 10 mu is 0, so that cancels out nicely. So what I'm going to then do is take away the 155 over to the other side and add the 580 over to this side. And then divide through by 580. And just quickly get my calculator out. And I will get lambda equals 1/4. Okay, excellent. I'll probably need to find mu as well. So I'll plug this back into one of my equations. So let's use the first one up here. 200 take away 80 lambda. Lambda was 1/4, so that would be take away 20 equals minus 20 add 10 mu. So from there we have minus 20s on both sides, cancel them out. 200 divided by 10 mu is 20. So what I now need to do is, at the value lambda equals 1/4 and lambda equals 20, my x and y coordinates are equal. But for the two flight paths to intersect, I need to check that the z-axis is also going to equal each other as well. So for A, let's call it z subscript A, I need to do 5 add 1/4 of 8, which is going to be 7. And for ZB, my coordinate is going to equal 5 add 20 lots of 0.1. 0.1 is the same as a tenth. A tenth of 20 is 2. 5 add 2 is 7. Great, so they both have a z coordinate of 7. So we know they intersect. All that's left to do in part A now is determine the position vector of the point of intersection. So lambda mu would equal 20, lambda equals 1/4. So let's use these equations here. 200 minus 80 times 1/4 will equal 20. 200 take away 20 is 180. And for the y one, it's going to be 200 take away 20 take away 100. 20 take away 100 lots of 1/4. So that's 25. 20 take away 25 is minus 5. So the position vector at which they will intersect is 180 minus 5 and 7. Excellent. So the next thing we need to do is to answer part B. An air traffic controller states this means the planes will collide. Explain why this is not necessarily correct. Well, the answer's in the mark scheme, so I'll just read it out. The planes pass through the same point, but not necessarily at the same time. So what could have happened is plane A could have travelled first, and then half an hour later plane B could have come along and intersected the same coordinate that A had previously crossed half an hour ago. If we treat these two values here as time, from a time period of 0, Lambda will have crossed over that coordinate at a quarter. Let's say the time variable was in hours, so it will have crossed it at after 15 minutes. But then 20 hours later, or nearly 20 hours later, plane B will have crossed it. So yes, they will have crossed the same coordinate, but not necessarily at the same time. That's what you need to write for part B. 9 marks.